In part one, we previously discussed that the kinetic energy of an electron emitted from a metal is equal to hf, which h is a Planck's constant, f is a frequency, minus the work function. So in this case, the work function is actually is equal to h times f0, which is the threshold frequency, the minimum frequency that we need to get the electrons emitted from the metal. So how do we demonstrate that in an experiment? So what we use is we use a discharge tube. So obviously discharge tube will have got two electrodes, cathodes and anode, and it's connected to a battery. So here in this case, that is cathode and this is anode, and so we have got it's connected to it to apply a voltage. And also we are going to have an ammeter in the middle here. We'll have an ammeter. So that'll be for the cathode, we are actually going to use different metals. So in this case, we use a metal which will be able to emit electrons when we shine a light or when we apply an electromagnetic wave. In the previous experiments that we are familiar with, the discharge tubes, we get the electrons emitted by applying high voltage. But in this case, we are actually going to get the electrons emitted by getting exposed to some electromagnetic waves, light waves. So what would happen is that when we apply these waves, electrons will get emitted and they will move towards anode. So all these electrons will move toward anode. At the same time, we will also see a current flowing this way. Okay. So now, what we are going to do is, we are going to reverse the polarity of this battery, because at the moment it's getting here, right? We want to push the electrons back from anode to cathode. Why do we do that? Because we want to find out how much energy is carried by these electrons. So to find that, there's no way to find out by just using any other instruments. That this is the best way to find out is to send these electrons back to this cathode. Then the current here will come back to zero. So when the electrons are moving from cathode to anode, we are getting a current here. But when we reverse this polarity here, so these electrons will come back to this place. So what we are going to do is, we are going to, this voltage is going to be like that. That means that the cathode will point to this direction. So this will oppose the electrons this way. So let's say that the voltage that we apply in the reverse direction to stop the electrons or to get the electrons back from anode to cathode is equal to V. So we call this stopping voltage. That means we are stopping the electrons coming to anode and sending them back to cathode. So that's a stopping voltage. Voltage is V. So what we are going to do is that we apply waves at different frequencies. So at the moment it's red. We change it to blue or green and different wavelengths and that they are different frequencies. And also we are going to use different metals here. So different metals will behave differently. That means that every metal have got a different threshold frequency, that you need different frequencies to get the electrons emitted from different metals. Now, from the stopping voltage, how do we find out that how much energy is required to stop the electrons coming to the anode? So we use the standard formula, that is the work done is equal to the charge times the voltage. So the charge of an electron is 1.6 times 10 to the power 19 coulombs, and that will be in joules. So we have a unit called electron volt, which will be quite useful, and that's a unit that we normally use for energy. Electron volt is that the energy or the work done on a charge of electron, and when it goes through one voltage electric field. So which means that the work done will be, in that case, it'll be, so 1 electron volt is actually, when you send a charge 1.6 times 10 to the power 19 times 1, so which is 1.6 times 10 to the power 19 joules. So 1 electron is equal to 1.6 times 10 to the power 19 joule, which is quite useful for this type of experiments. So now let's look at this graph here. And we have got three different metals, a red, green, and yellow. And every one of them, so this is on x-axis, we are having frequency and the maximum kinetic energy. So for red, at a particular frequency, you see that the kinetic energy is 0. So that means that's the threshold frequency for red, and this is the threshold frequency for green, and that's for yellow. So anything more than that, that will provide more energy for that electrons. And if you do an experiment where you're going to have different frequencies and measure the energy, and this is a bit you will be doing above 0. So if you extend that line after getting these points, so when you do an experiment, you have all these points here, and you draw the line of best fit, and they all meet here, right? So if I say this is X, this is Y, this is Z, different metals. So this is the threshold frequency for Fx. I'm going to put F0 Fx, and this is F0y, and this is F0z, and that's the threshold frequency for all three metals. And this one is the energy that's required to just get the electrons out. So that means that is the work function. So we can say that one as phi x, and the same way this is phi y, and this one we can say it's phi z. So doing these experiments, that we can find what the work function is, and also we can find the energy at different points, at different frequencies. So for this metal, at a particular frequency, we know how much kinetic energy is carried by that electron. And there's another interesting one we can find from here, is because we know that equation is the kinetic energy is equal to HF minus this one. So this is in a form of y is equal to mx plus c, right? So this is y, and if this is x and this is m, and that is c here. So once we draw the graph, the gradient of the graph will give us the value for h. So h is the Planck's constant, and which is always given by 6.63 times 10 to the power minus 34. And this is the constant value that we normally use to solve problems that is to do with the photoelectric effect. But if it is an experimental one, we can find the Planck's constant doing this experiment and drawing these lines and finding the gradient of it.